right, Advent of Code 2019, day 12, about to start. What do we got? Jupiter, moons, position of the moons, simulate their motion, 3D position, 3D velocity, time steps. First we do gravity, then we apply velocity. Gravity affects the velocities. Velocity plus or minus 1 pull together for each pair. Okay. Total energy, potential, sum of the absolute values, sum of the absolute values of the coordinates. Okay. This is day 12? Yeah. There's 4 of them. Okay. Okay, parsing done. So, every time step Energy multiplied by its kinetic energy. Alright. Cool. Previous point in time. These. Okay, so what's going on here? Okay, so what happens if we have just two things? They go towards each other. Eventually they slow down and come back. actual way to do this. This is billions. It's not that many. All the dimensions are separate. Okay, so that's y. Okay, so y repeats after that many. Oh my gosh. Okay, that was a really cool part too. Okay, so what was going on here? So we have as input these four three-dimensional things with x, y, and z coordinates. And so we beat them in and we parse them, which is really kind of a pain because of this input format. But anyway, you know, each one's on a line. We remove the left and right angle brackets. We split them into words, and then for each word, we split an equal sign. Anyway, there's probably a better way to do this. I mean, there's definitely a better way to do this. But anyway, it works. Anyway, we set the starting positions. The starting velocity is all 0. So now we have the list of positions and list of velocities. Okay, so now for the interesting part. Yeah, so I guess this is just for part 2. Actually, let me fix up the code for part 1 as I am explaining. Is it 14780? Yeah. Okay. Is that the right answer? 279592? Yeah. Okay. Sorry. Delay there. So what's going on? So we read in the input. Now here's how we simulate a tick of time. So it's for each pair of moons, and then for each coordinate, we want to change the velocities so that they get closer to each other. So if we are less than the other guy on this coordinate, our velocity increases by 1 on this coordinate. And if we are more than this guy, then our velocity decreases by 1 on this coordinate. And if they're equal, then nothing happens. It's also if j equals I. And then we just apply the velocities. So for each moon and each axis, the position increases by the velocity. Okay, that's how ticking works. So for part 1, you just tick 1,000 times, and then you add up the energies. So the potential energy is the sum of the absolute positions. The kinetic is the sum of the absolute velocities, and then you multiply them together and add them up. Fine. Part 2, trickier. So part 2 says how long until they repeat, and it warns you it could be a very long time, which is the case for us. So my key insight for part 2 is that each of the axes is independent. Right? What happens on the x-axis is totally, it's totally unaffected by what happens on the y or z axes. Right? Because if you look at how this works, like the x-axis only depends on stuff that's going on in the x-axis. So we can handle these as 3 independent problems. And this is a good idea because they're going to repeat much sooner across one axis than across all 3 axes. That's the hope anyway. And that turns out to be true. So what do I actually do? So I'm going to look for all 3 axes to repeat. Take a tick. So figure out what is our current position and velocity in each axis, right? This is the thing that we are looking for a repeat in. This is just so it's hashable. It's a Python detail. And then across each axis, x, y, z, if we've already seen it, then check that it always repeats from 0. I don't actually know why this should be true, that it repeats the starting position instead of some later position. Maybe maybe you can run this backwards. Maybe. Anyway, it does happen to be true that it always repeats from 0, which is nice because that means I just wrote down the key claim. So why is that true? So if x repeats every 10 steps and y repeats every 7 steps, then after 70 steps, right, x is again in repeat because it repeated 10, 20, 30, 40, 50, 60, 70. Right? If it's the same as it was at 0 after 10 steps, then it's going to be the same again after 20 steps, right? Because it started from the same place and went another 10 steps. And similarly, y is also going to repeat after 70 because it repeats on every multiple of 7. So how do we find out when they both repeat? We need to take their LCM because they both repeat if it's a multiple of both of their periods. So the LCM is just the product over their GCD. Yeah, I think maybe I won't try to explain why that's true. Maybe it's not so bad. So the LCM is supposed to be a multiple of both of them. So certainly tx, ty is a multiple of both of them. but there may be some wasted sort of repetition there because not sure how to give your intuition. Okay, well, I'll just give the math formula. So if you look at the prime factorization of tx and ty, if you have p and p squared, say, for some prime, then you only need p squared to be a multiple of both of them, because this, I don't know, p squared is already a multiple of p. Okay, I'm explaining this quote. Anyway, this is a true thing. Okay, so we just update part 2 to be the LCM. It's also true that the LCM of ABC is the LCM of A and B with the LCM of C, so that's what's going on here. Yeah, so we're finding the period of the x-axis, period of the y-axis, period of the z-axis, and we're just taking the LCMs of all those periods, and that gives us our final answer, which is super big. It's way bigger than they warned us about, right? Thousands, millions, billions, 279 trillion ticks. Definitely was not going to get there by brute force. Yeah, so this was a cool problem. Definitely required some thinking in part 2. There are just sort of 2 claims that are important for my solution that I don't know how to prove. One of them is that it always repeats starting from 0. Right? You could imagine, that the 10th thing is the same as the 5th position, but not the same as the 0th position. But that doesn't happen. It always goes back to the starting point. That might be not that hard to prove. If you can reverse the time, then that has to be true. That is, given the 5th position, you can figure out the 4th position. Why would that prove it? If the 5th position only has one possible previous position, then the 10th position can't equal the 5th position without the 9th position equaling the 4th position, and so on down to 0. Yeah, okay, and I suppose that's the case, right? Because given a position, you know that its predecessor has position minus the respective velocities, and then you can sort of reverse the velocities by the positions. Okay, so that's why that it always repeats from 0. The other claim that I need to be true for my solution to work is that each axis actually repeats in a reasonable amount of time. So why should that be true? Well, we have 4 things, so that gives us 8 numbers on each axis, right? A position and a velocity for each of 4 things. I don't know, each thing probably can't get that big, because, I don't know, basically if you go too far in one direction, you're going to get pulled back by the gravity of the other moons. It's pretty cursory analysis, though. So yeah, I'm not really sure why that part's true. Okay, well, we've been talking about this problem for quite a while, so let's stop the video here. And if you can prove why each axis should repeat quickly, please let me know in the comments. All right, that's day 12. Really cool day.